Okay, so we're going to work on Swiss time today, which means that as it went 3 o'clock in South Africa, we're starting. I'd like to welcome you all. Probably not everyone knows me. In fact, I'm sure not everyone knows me. My name is Craig Sheridan. I'm a professor at the University of the Witwatersrand in Johannesburg. I hold the Claude Leon Foundation Chair in Water Research, and I direct our Center in Water Research and Development. So there's a reason I'm presenting this, is that Margaret and I together are co-hosting a conference in WITS as well as at WITS Rural Campus next year. I'll chat about it in a second. But that leads to the reason that I'm sitting here specifically with this view, is to sort of share with you the sunshine and the good weather we have here, which is actually to encourage you all to have a look at the IIES website and to register for the conference, so that you can at least get a sense of what it's like here in South Africa. So with that, I'd like to welcome everyone. This is the first of a series of lectures that we're running for the 2024 cycle. This series is co-funded by Europa through the Europa Africa grant. It's co-funded by the International Institute for Environmental Studies, as well as the Claude Leon Foundation. And as I mentioned, it includes a 2-day conference at WITS University, followed by a 3-day graduate workshop at the WITS Rural Campus in Mpumalanga next year in April. And that campus is about 15 minutes drive from the Kruger Park. So I will encourage you to please go to the IIES website for details. I also want to acknowledge Dr. Sarah Donahue for her hard work in putting together the Teams link, as well as Ms. Raquel Scott at Trent University. Sarah's at Edinburgh. Without the two of them, I'm not quite sure the logistics for today's call would have happened. So I'd like to say thank you both very much for that. And you will be in touch with them both over the course of the next sort of year as we have these lectures and with the conference. So it would be nice, you can at least get a face to go with their names. So with that, I'd like to welcome Professor Margaret Graham to present her lecture. Margaret is a professor in environmental geochemistry in the School of Geosciences at the University of Edinburgh. Over the past few decades, she has developed a cross-disciplinary research network in the area primarily of environmental biogeochemistry. The main themes of her research are natural organic matter, character and function, contaminant geochemical behavior and the impact of ecosystem and human health, development of novel laboratory and analytical methods, and fit-for-purpose field remediation approaches to mitigate the impact of potentially toxic elements on the environment and on human health. Her research has an extensive international reach, including collaborators in Canada, China, Finland, Sweden, Switzerland. That's why we were working on Swiss time today. Thailand, and now it also includes South Africa, because we have a very nice program that we're working on. Margaret, I'm not sure if you're still the associate director, but she was the associate director and executive board member for the International Institute of Environmental Studies, which is a virtual network of leading environmental research teams from around the world. So her lecture is entitled Climate Change Induced Pressures on Water Quality in Scotland. So I'd like to welcome you to this. If you wouldn't mind holding your questions till after the presentation, and then you can go live and ask Margaret in person, I guess, or you can drop them in the chat box if you feel like it. But otherwise, Margaret, over to you, and thank you.
Thank you very much. Let me just start by sharing my screen.
It's nicely shared.
Excellent. Okay. So thank you very much, Craig, for setting the scene for this lecture series and for the very kind introduction. I'm delighted to be giving this opening lecture, and I'm really looking forward to the entire series. It's going to be a great chance to learn about different approaches to address water issues around the world. So today I am going to give an overview of some of the problems that we currently face in Scotland. My presentation will include research that we have been doing in conjunction with Scottish Water. They are our local water authority with responsibility for our drinking water. But I'll also look back at some work that we did not long after I started my academic career, and that seems to be 30 years ago now, time does fly. So to explain the backdrop to the ongoing work, Scottish Water initially contacted me in 2021 because we were experiencing near drought conditions in some parts of the country, and there were reports of water quality problems, especially in the west of Scotland. Now, Scotland is not typically a country that you would associate with drought, but predictions are suggesting that there is an increased risk of extreme drought, and that is where exceptionally dry conditions persist over a large part of each year, say from March through to November. So here's an example of what we saw in 2021. So these maps show the United Kingdom with Scotland at the top, and they represent the rainfall as a percentage of an average that was taken over the period 1981 to 2010. And the more intense brown colours represent the lowest rainfall. So you can see, especially in western areas of Scotland, and these are the ones that we typically find are normally the wettest parts of our country, in this period we had significantly lower rainfall compared to that mean value. Indeed, in the summer, where the very dark brown colours are, it was less than 30% of the expected values. So the last slide was 2021, and this one is for 2022, showing sunshine on the left, rainfall in the middle, and maximum temperature on the right. So you can again see that many areas had only 30% of the normal rainfall and up to a 2-degree increase in mean maximum temperature. This combination of warming and reduced rainfall has led to concerns about the risk of harmful algal blooms. And the greatest effects are expected, first of all, in southern Scotland, but by 2040, it is predicted that these will impact all regions of Scotland. And a major worry is that the blooms may restrict the use of some of our water supplies. Against that backdrop, however, we have also been experiencing the opposite extreme, exceptionally wet conditions just before and after the drought period shown here in 2021. And similar extremes have occurred in subsequent years. And here are some examples. In the north of Scotland, flash flooding causing rivers that don't have a history of bursting their banks to suddenly show high flow conditions. And then central Glasgow, this was just before COP26, with the weather providing some challenges for our international visitors, but plenty for the ensuing climate discussions. Overall, however, the average annual rainfall in Scotland is sitting around 1,500 millimetres per annum. But what we're seeing is an increasingly spiky pattern and very low values, mainly occurring since 2020. Now, these used to be a once per decade occurrence, and I looked back, and it used to be, for example, as I say, once a decade, 1985, 1995, 2003, 2010. But then you see the ones that I've highlighted in brown here, so that's 3 in about 4 years, where we're seeing exceptionally low rainfall conditions, especially in summer periods. So what did this mean for Scotland's drinking water? Well, we have over 30,000 lochs in Scotland. Now, loch is the Scottish word for lake, and we use somewhere between 100 and 200 of these for our drinking water supply. And they were particularly badly affected during this period in 2021. So this is 2 examples: the Black Esk Reservoir during the summer period, but Dar Reservoir you're seeing there, that's from autumn. And as I said earlier, the water levels dropped significantly. That was about 9 metres below the normal levels, equating to only about 35 to 55% of storage capacity. Here's an even more extreme example. This one is from Perthshire, I think maybe quite close to where Sarah is based. And the water level here dropped by more than 40 metres. and it fully exposed a farmhouse which had been underwater for 65 years. And as before, these dry conditions prevailed until the late autumn, so right through almost into November of that year. And what followed was significant concern about drinking water quality. People in Ayrshire in the west of Scotland were reporting what they called dirty brown water. And this is an example of the water that came from a Dar reservoir that I showed you just a few moments ago. And Scottish Water had to provide bottled water while they reassured the public that the problem was being fixed. They explained that the water levels had reached historic low levels, and unexpectedly manganese concentrations had gone up very rapidly, and essentially their treatment plants simply weren't able to deal with these very high levels. Why does this happen? Well, manganese is a bit like iron in that both of them have soluble and insoluble forms in aquatic systems. For iron, iron 2 is soluble under acidic conditions, but it oxidizes very rapidly, especially around near neutral conditions, and it easily forms insoluble iron oxides or hydroxides. So its chemistry is easy to manipulate to effect removal. The manganese also has a +2 oxidation state, and that form is soluble, but it oxidizes much more slowly, so it might take periods of weeks to months for manganese to oxidize to the insoluble forms. And so soluble manganese is difficult to remove during conventional water treatment work, especially under the conditions that we find in our Scottish waters, which tend to be slightly acidic to near neutral. So why is this a concern? Well, it's certainly a concern for the aesthetics. People don't like to see the brown water. They get worried about that. But it also causes staining of clothes in washing machines. So, for example, what happens is that manganese oxide nodules form within the washing machine, and if you have white t-shirts, then they come out with dark brown patches on them. It's also a problem for water distribution, as precipitation of these manganese oxides within the pipes causes water pressure or the water flow to drop. And the UK and EU drinking water limit of 50 micrograms per litre is largely set to limit these problems. We are also finding that manganese is partly causing problems in water treatment, and this is an example from a recent publication from one of my past PhD students, Desislava Davidkova, and this is taken from her 2024 publication in Environmental Science and Technology. And what she was looking at was nanofiltration membranes in remote island water plants. And what they were finding is that they were failing much before their recommended lifetime. And these failures are linked to a combination of biofouling and the buildup of both manganese and iron on the membrane surfaces. And if we look at the bottom right diagram, that shows the fluorescence image of the membrane and of the extracts from the membrane. And then on the right hand side, we have a scanning electron micrograph of the membrane itself. And so the fluorescence, the more intense yellow colours, are showing where the main emissions are, and these are related to aromatic proteins and soluble microbial byproducts. And the SEM image, which is much less clear, you might have to take my word for this, but you can see rod-shaped bacteria on the surface of that. So what we're seeing is biofouling, and from the metals analysis we did by ICP-MS, manganese and iron associated with these dark patches on the membrane surface. But what about human health? Well, exposure to higher levels of manganese, and in relation to the old WHO, the World Health Organization limit of 400 micrograms per litre, If we were going beyond that, then the health effects for adults is something like a Parkinson-like disorder or manganism. For children, however, they are affected at lower levels, and declines in their IQ levels and behavioural problems are reported at much lower levels than that. And the most recent studies are suggesting that levels in the low hundreds, maybe even less than that, might be harmful to younger children. So the World Health Organization has reduced its limit to 80 micrograms per litre, and this applies now to all age groups, not just to children. So you can see why there's a concern, and Scottish Water came to us with a very large data set and asked us to try to explain why we would be seeing high concentrations of dissolved manganese in water during the summer and late autumn periods that I have shown you. So they gave us data from 2005 to 2021, and then very recently they also gave us some additional data for 2022 to 2024. So they wanted to know why we get high concentrations, and also why it was happening in places where there's never been a history of previous water quality failures. And in this slide, I've just summarised all of the data, and the table shows you the mean and median manganese concentrations and the number of analyses that they made. Now, in the early periods, the frequency of sampling was quite limited, and it also wasn't particularly routine. So we really focused on the more recent periods from 2016 onwards, where there were more than 1,000 analyses per year. And what we can see is that the median concentration stays in the range of about 2 to 5 micrograms per litre if we take it right through to 2024. But the average concentration is sometimes a bit higher than that. So somewhere in the range of about maybe 6 up to 17 micrograms per litre. And you can see that I've also plotted this on the left, and the dots represent the 5th and the 95th percentiles of the data. And particularly you can see from the 95th percentile that there must be quite a lot of higher numbers in there, even though we're seeing quite low mean and median values. So the mean and median would sit well below the limits, but clearly there are some higher values hidden in this data set. So what we did next was to then pull out all the data for individual years, and I'm only going to show just a selection of these years. I'll show you 2020, 2021 and 2023. And the black line across my graph shows the point where we reach 50 micrograms per litre, and I'm just going to use this as an indication of when the concentrations go high, so they go above that line. So for 2020, you can see it was a good year for Scottish Water in that we didn't have many samples where the concentration went greater than 50 micrograms per litre across any part of the country. But in 2021, the year where we had the intense drought conditions, you can see a very different picture. And you can see clustered high concentrations from midsummer right through to late autumn. There's 2023 data, and again, what we're seeing is a predominance of high values in the summer and the autumn. So we drilled down a bit further, and what we found was that a lot of these failures come from a relatively small group of reservoirs. On the map of Scotland, you'll see 5 in the west to the southwest, and then 2 in the east and the northeast. I've pulled out their annual patterns, and so you see the series of graphs from Braddon on the top left down to Roberton on the bottom right. And I've highlighted the summer and autumn period, and you see again in every case that the elevated concentrations of manganese occur in summer and into autumn. We see in spring and winter often very low concentrations, maybe only 2 to 3 micrograms per litre for some of these, and then a rapid transition to very high concentrations. To give some scale, I have put on the various limits. So the black line is the EU limit for drinking water. Then the blue lines represent a drop of 1 and 2% in IQ. And then the red line at the top shows the old WHO limit. So you can see that none of the waters exceeded that high value of 400 micrograms per litre, but in many cases we were well above the EU drinking water limit. So I told you that this data was the year 2021 when we had the drought conditions. So the next question was, is the elevation in manganese related to the drop in water level? So I've taken several of these problem reservoirs, and the blue line represents the water level and the red line represents the dissolved manganese concentration. And so in all cases, we see that the high concentrations occur during the period of low water level, but there's no threshold level triggering release, and there's no consistent relationship between the drop in level and the maximum dissolved manganese concentration. To add to the complexity, we find that there are some reservoirs where manganese failures occur every year, and at Loch Braden, that is very much the case. So this is something that a treatment plant can prepare for because we know to expect high concentrations at certain times of year. However, it was a new problem elsewhere. And I've mentioned Dar Reservoir before, and that was the one that was linked with the dirty bathwater. And this was the first time in 2021 that there had been a problem at Dar. So you'll see the 4 graphs I'm showing here for 2018 through to 2021. I have expanded the scale considerably for the first 3 of these. So you can see up to 20 micrograms per litre for 2018, for example, and only up to 7 micrograms per litre for 2019. We see the same trend every year, so it's almost like this effect was under the radar. We didn't see it because in the previous years it was below the limits, so there were no water quality failures. But in 2021, you can see that I have the black dotted line, and for long periods from September through to November, we had concentrations in the range of 50 to maybe 110 micrograms per litre. As I say, this came as a surprise because there was not a history of failures, and therefore the water quality plant was not prepared to deal with that. We also looked to some other factors, and I mentioned that when I showed you the maps that temperatures, especially in summer, were warmer, maybe up to by 2 degrees. And Scottish Water doesn't have very much temperature data, but we were able to get some water temperature for 2 of the plants, Loch Braden and Loch Dar, the ones I've just been showing you. And so we see the seasonal patterns for temperature at the top, and these would be as expected. But then if you look at the dissolved manganese concentrations down the bottom, yes, we do have higher concentrations during warmer periods, but there is no direct relationship to temperature. So it's not to say that temperature won't be part of the story, but it's not the only explanatory factor. Other things we can look at, I mentioned when I was talking about water treatment and the behaviour of manganese and iron, I mentioned the importance of pH. And I said that the source waters are slightly acidic to neutral with pH range of about 6 to 7. But we also looked around these reservoirs, and what we found was that the problem reservoirs were mainly in acidic peaty areas. So you'll see on the map on the left that the more intense red colours tell you that we are very acidic, and many of the reservoirs sit right on top of these acidic areas. And then if you look at the soil map from the right, you can see the colours. The purples relate to peat, and the reds relate to peaty podzols. So we've got very organic, low pH conditions, and then we can also see the colour of the water in this slide here, and this is the inlet water to Loch Braden. So it's very highly coloured waters that we have. Now the map on the left might look very similar to the one I showed in the previous page, but there I was showing pH, and here what I'm showing is the stream sediment concentration of manganese. And so another factor is that we're in relatively manganese-rich areas. And this is down to secondary mineralisation processes rather than the underlying geology. It may be that geology is important, but there's also this other factor of acidic conditions, streams with high manganese, and then piecing that together, we have highly organic conditions as well. And the consequences of that are that we find that we have a build-up of manganese in the reservoir itself. And I'm just showing you one example here of a sediment core that I collected many years ago, and one of my PhD students, Helena Engler, who's on this meeting as well, she is working there now and will have more recent data. But what we are observing from my previous work was that we have a trend in the direction of the water flow. So for example, at the inlet end, we have concentrations maybe up to 1 or 2% by weight in the near surface sediments, but by the time we reach the outflow, then the black line shows you that we have nearly 10% by weight of solid phase manganese in the first few millimetres of the sediment. Then if you look at the red line, that shows the pore waters in that same sediment core, and the concentrations of dissolved manganese are up to 20 milligrams per litre, and that's not an incorrect unit, that's actually 20 milligrams per litre in the near surface top 1 centimetre of the reservoir sediments. And if we project that into the overlying waters, what we are finding is diffusion out of the sediment into the water and concentrations from this core of 200 micrograms per litre. Now I say that's old data, but it just gives you an idea of what might be happening in terms of the release of manganese into the reservoir water. So what we then put together was a set of risk factors, things that we think would help to identify which of the reservoirs might have high dissolved manganese. And we found these as common features for our suite of reservoirs, and these are things that I've just talked about. So the low stream water pH, the high stream sediment manganese, the highly organic catchments. Not only are the catchments highly organic, but the sediments, I showed you the sediment core, but these sediments in the bottom of the reservoir, these also have very, very high organic matter content. And the reason for this is that they used to be smaller natural water bodies, but many of them were extended in order to increase the volume of water that they could hold. And so we have peaty soils at Braden and at Dar, both now having a significant amount of submerged peat. And recent work that I'm showing here, not our own work, but by Traynor et al., is pointing towards the important role of certain kinds of organic matter in changing the speciation of manganese. And what is shown in this schematic from that paper is the transformation of aromatic organic matter, and at the same time the reduction of manganese 4 to manganese 2, but maybe also to manganese 3. And so we think it's going to be very important going forward from here to understand the interplay between pH, redox, the dissolved organic matter transformations, and manganese behaviour. So to take this forward, we also need to try and fill in some gaps in existing data sets. And one of the things we found when we were looking at the Scottish water information was there's very little, if any, dissolved oxygen data available. And that's something we have looked at in other studies as being a key factor in the release of manganese, but we just don't have that information at the moment. Our past work in the 1990s at Loch Braden, we didn't find any difference in dissolved oxygen throughout the entire depth profile. And our lakes are very shallow, so maybe only about 12 metres depth at Braden. But at that time, we didn't have the opportunity to study a period when the water levels were particularly low. But Helena's exploratory work this year suggests that there may be a decline in dissolved oxygen from the surface to the sediment interface, but that the trends are not as pronounced as shown in the diagrams from here. And I've taken these examples from Australia and from other countries. So overall, I think we really need to learn much more about how shallow reservoirs respond to seasonal changes and how this affects the behaviour of elements such as manganese. We think it will be very important to distinguish between manganese 2 and manganese 3. And that's something that might be quite difficult to do at the moment. There are examples in the literature, and there has been work done in marine systems, but there's much less been done in freshwater environments. But there's a little information starting to come through in northern England from water treatment plants that suggests that they are observing both manganese 2 and manganese 3. And so that's maybe something that we can explore much more and try to improve the robustness of methodologies to make that distinction. And this example here from a paper in Water Research 2022 shows the algal-derived organic matter. And I think hopefully if you remember at the beginning of my lecture I was talking about Scotland might in the future have an increased prevalence of algal blooms. And this paper considered the links between the algae and some of the other parameters that I've talked about with pH and with dissolved organic matter and also with iron. That paper didn't talk about manganese, but that would be obviously the step that we would be interested in. And one thing to note here is that this paper also looked at the changes in the organic matter, and again identifying that aromatic organic matter might be particularly important. And as part of Helena's PhD, she will investigate the use of advanced NMR techniques and Fourier transform ion cyclotron resonance mass spectrometry to try to get a better feel for the composition of organic matter, both in the sediments and their pore waters and in the very bottom waters. And that's something that we intend to do next summer in our final field campaign. So better understanding of these shallow reservoirs, if we can do that, then we may also then be able to feed that into our understanding of what the best options for controlling manganese might be. So if conventional treatment plants are not able to cope with dissolved manganese, then maybe there's a solution that can be adopted in situ. And this is just one example of these. So this is from the literature, and it's a hypolymnetic oxygenation system where oxygen is introduced towards the bottom of the reservoir. And this was done in the US, and the reservoir depth I think was a little bit deeper than what we have in Scotland, but not particularly so, maybe about 20 metres rather than our 12. But what they found was that this had a very good impact on dissolved iron concentration. So you can see from the right images, you see iron above two graphs. The top graph shows total iron and the bottom graph shows dissolved. So you can see almost no dissolved iron. But for manganese, the graphs on the left you can see that there's not much difference between dissolved and total manganese. And so even under relatively oxygenated conditions, manganese is able to continue leaking out of the bottom sediments. And if you remember back to my sediment profile, we had high concentrations very near the surface, so 20 milligrams per litre just in the top centimetre. And diffusion away from that is providing a continuing source of manganese to overlying waters, for example. And other studies have reported hypolimnetic oxygenation to work very well, but the distinction is for these studies that the pH range was much higher, so maybe around 8 or even a little bit higher than that. But the study I'm showing here, the pH range was about 6 to 7, so very similar to actually what we observe in the Scottish water scenario. So based on just on this alone, we would say that this method would not be a suitable approach for controlling manganese in the Scottish environment. So overall, I think it seems fair to say that we are going to experience increasing water quality issues in the years to come. We can see the changes in our climate, we can see the more extreme weather conditions going from very, very stormy conditions, very intense rainfall periods, and then interspersed with very long periods of almost drought conditions for Scotland. We have considerable evidence to support the seasonally related rapid release of dissolved manganese from the bottom sediments into overlying waters. And this is occurring in shallow lochs, which have a high degree of colour and are slightly acidic to near neutral, and also have very organic rich catchments. Although from the evidence this is likely to be redox related, we don't know the detailed mechanisms, and we need much better understanding in particular of the conditions prevailing at the sediment water interface. Now that's very hard. The water authorities, that's not somewhere that they're able to look. They collect water samples at the inflow to their water treatment plant. They may also take them just a spot sample from some point near the surface of the reservoir, but they are not routinely monitoring near the sediment water interface. Even with our research equipment, it's quite difficult to do this. But it's really important, and especially to get at the processes involving the organic matter. We also think that we should direct efforts to understanding the role of microorganisms, because there's building evidence that microorganisms are also involved in the processes of changing the speciation of manganese. Given the recent reports, we should look for connections between metal cycling and algal blooms. And in Scotland, these are likely to become much more important over the next decade. And finally, we need robust methods for determining speciation of manganese. And we think that it's not just sufficient to assume that dissolved manganese is manganese 2, and we need to look at manganese 3 and its role in this behaviour that we're observing. So thank you very much, and I hope I will be able to take some questions now, and hopefully be able to answer your questions, so I'll stop sharing my slides.
Thanks, Margaret, very much. I'm going to ask everyone if they will just use the raise the hand icon like I've just done. It's on your toolbar on the top if you have a question. Margaret, because I jumped in before everyone, can I ask the first question?
Yes.
Well, it's so interesting what you've just done. And I was thinking, while you were talking through your presentation in particular, I was wondering about the effects of oxygen and then the solubility of oxygen as a function of temperature, and how these all interplay as your lochs get lower because of drought and higher temperature. And I mean, it's a particularly complex triangle, that temperature, solubility, redox potential, and then you start looking at the manganese solubility as a function of the redox and the oxygen levels. So, I mean, I know that's the work you're going to do, but it seemed really interesting that those factors are coming together at the same time.
Yes, and I think that's what we hopefully will be able to collect more data next year. This has been a particularly difficult year because this summer was incredibly wet, and so it made it very problematic for us to deploy equipment. So we do have some initial data that will start us on that journey to piece together the temperature, the dissolved oxygen, and the other parameters. But we're just not in that position yet. But I think for shallow lakes as well, much less is understood about just how they change seasonally. And how, for example, do they have a the change in oxygen from top to bottom? Is it different from deeper reservoirs? We think so, yes, but how? And how does this then affect some of the other parameters that we're interested in? But we just don't have that information. And a lot of what I've done is piecing together evidence that is somewhat remote from the reservoir, because I'm taking data that Scottish Water has given me from near where they abstract the water.
Yeah.
But now we are able to work in the reservoir itself. But it's a long process, and it's a matter of just building the pieces of evidence gradually, and just hoping we get a good summer next year.
Yeah, and I guess as well, I think it's striking that in an age of emerging contaminants, how climate change is making legacy contaminants become an issue again. For me, that was just the other observation I had, which is fascinating.
That's also true because we have arsenic concentrations for the sediments, and the cycling of that is also very close to the surface. And we don't have a lot of measurements for the water, but we know that some of the other catchments that we're working on in Dar, there might be even slightly higher concentrations, but we don't know how the arsenic is behaving. But we could make some calculations about what might happen if the manganese and the iron phases dissolve, and the potential, like the maximum amount that could be released. Obviously, then we might expect some reprecipitation, but you're right about the legacy from coal burning. We have lead, we have arsenic, we have other elements.
Yeah, thanks. Julian, your hand is up first. Do you want to go?
Yeah, I will. Thanks very much, Craig. Margaret, sorry, I've got a bit of a cold, so my voice is a bit croaky, but very interesting presentation. It's a great comment by Craig there, in that I look forward to seeing your presentations to do with lead and arsenic in the future. But with reference to this one, it wasn't, or at least it wasn't clear to me, or I wasn't sure if the water is if there's direct abstraction from the reservoir, or if it's downstream. And if it's downstream, how much of a burden comes from the stream itself as well? So that you've got the stream and the stream sediments acting as a source of manganese.
Well, we've got an inflow from a river, because particularly at Loch Braden, it's got an extended catchment, and so the River Stincher brings a lot of organic material with it. The Scottish Water, where the abstract is at the opposite end, and there's a dam, and we don't know exactly the depth that they abstract from, because that information is sometimes not recorded, and it may change at different periods during the year. And a further complicating factor is that they link together several reservoirs. So it's not always just one reservoir water. It could be two or three. In Braddon, for example, there are two or three different water bodies that are mixed together and then treated. And the information sometimes about how and when they mix is not absolutely clear. What I can see, though, is I can see source water and I can see raw water, and also there are some codes, so we can start to pick it apart, but it's not an easy process.
Yeah, so it could be inflowing streams that are bringing much of the burden. The second question I have is, if I can have another question, Craig.
Yeah, sure.
That I mean, it's clear that the organic soils are one of the issues, But that's not a uniquely Scottish problem, I assume, and that maybe Wales, Northern Ireland are seeing the same thing.
Yes, that's correct, and certainly for Ireland. And do I remember correctly? I think I did speak to Welsh Water at a Scottish consortium meeting, and they also had noted similar problems, but definitely for Ireland, Germany, other countries are reporting it as well, and certainly for the Irish situation, I think it is probably quite similar to ours. Not so sure about some of the other parts of the UK.
Okay, thanks very much. Very interesting work.
Thank you. And okay, thanks.
Yeah. Thanks. Erin, your turn. You're up next.
Hey, Craig. Just building off your question, Margaret, how are you measuring DO and pH? Have you considered using data loggers? So you can get a monthly or an annual picture of how the DO is? Yes,
that's what we're trying to use sondes and deploy them in the reservoir at fixed depths. We have been doing some of that work this summer, but we experienced some problems, one with the operation of these sondes. They're not as easy to use as we would have liked them to be. We've done some depth profiling, but then we experienced some very bad weather conditions, and so we weren't able to leave them in the reservoir for long periods in order to get that long time record. But yes, they can be set to do, I think, 15-minute measurements, or we can set them to hourly measurements, whatever we need to do. So yes, that's what we are trying to do.
Great, thanks.
Thanks. Sean, you're next on the list.
Hi, Margaret. How you doing?
Hello.
Great talk. A few years ago, I did a study in Ontario, so a bit away from Scotland, but similar, and looked at manganese over a 20-year period, and very similar to you. We saw these peaks in dry years, very high peaks in stream water. It was higher in streams that drain peatland or organic soils. And what I observed is that the most strongly correlated was sulfate. And the idea is that, during the dry periods, you get an oxidation, and then you get a pH release with water. Do you have sulfate data in your? Is that occurring in your place or not?
We haven't. To the best of my knowledge, we don't have sulfate at the moment, but it's certainly, we can make some measurements and make sure that gets included. We had stream water samplers set out as well, and we have some data. We can see that the manganese concentrations for some of the streams that are draining through the forested areas actually on the northern shore have extremely high concentrations of dissolved manganese, and we're looking into that in more detail so we can add in extra parameters for the analysis as we go forward from here.
Okay, thank you.
I'm really interested to hear that you have.
I'll forward you the paper so you can see it.
That's lovely.
It's great.
Great, thanks. And then the next question is Kate.
Hi, Margaret. Thanks very much for a really interesting and clear presentation. It seems a really complex system from what you were explaining, with probably interaction of processes happening within the catchment more widely, but also in the reservoir system itself. And you mentioned some possible solutions in terms of in situ reservoir measures, the oxygenation. But I wondered, a Scottish Water or in other areas, they're looking at sort of catchment scale measures as well?
I think they're looking at the catchment in Carron Valley as an example at the moment. And they're also exploring the use of bubble curtains, but that's the bubble curtains within the reservoir. They're not doing anything around the catchment where we're working at Braddon and Dar at the moment. But I think in the future they would like to consider what might be their best options. They made some investments in mixing res mix systems, but they're very expensive to operate, and they do have some problems for example, when you switch them off, the problem comes back very quickly, but also it might actually turbate the sediment and cause other issues for them. So ResMix, they took on quite quickly from what I understand, but maybe they might consider other options. So I think it might be a combination of catchment studies to look at what might be best. And I think the example at the moment is Carron Valley, which has a range of problems, not just manganese. So there's taste and odour and other things as well. And then building up from there to see what might be the best solutions for the different kinds of catchments that they have.
Yeah, that's great. Yeah, I suppose if you could predict when you might expect elevated concentrations in stream waters, if the infrastructure's there, you could potentially switch off some sources or not. Yeah, that's very interesting.
Yeah.
Thanks very much again, Margaret.
We found that, I mean, even for Braddon, the 6 streams are very, very different. And we know that 4 of them don't really have high values for a lot of the time. And then 1 of them is exceptionally high. But we obviously need to take into account the flow as well. But yeah, I think that would be, that kind of information we could feed into the Water Authority and then help them to make the decisions.
Thanks. And then we have another question. I'm sure I'm going to say this wrong, but it's from Kwong. Maybe you can go.
Yeah. Hello, Margaret.
Hello.
Yeah. Yes, I'm Khai. No, Kwong is my middle name.
Hi, Kai.
Okay. Yeah. You're very interesting. Yeah. This is the second time I saw the presentation, but I still have a question. Yeah, because I still worry because we saw some kind of the manganese mobilization during drought season, during very drought season. So you think that is related with sediment, the manganese released by the sediment in the reducing environment, right?
Yes, we think so, because the water flow coming in from the streams is very low at that time of year. And for these examples, the reservoir level has dropped by, it was in some cases up to 9 meters.
So it means that for me, I can I think that's because of during drought season. During drought season, the lake they don't have input water, so the oxygen is not be supplied. That you will indicate, you will create the reducing environment. Then the mangan can be mobilized, right? But do you check the because I also think the possibility of the manganese mobilization by groundwater recharge. Do you think
that is a question that we are asking, and Helena has been preparing samples to look at deeper waters. So we're looking at doing the oxygen and hydrogen isotopes. So that's something that she has applied for at the moment, and we hope to get the funding in order to do that, so that we could answer that question, because at the moment there's very little information in Scotland for us to be sure. And as you say, things point towards the sediments and the release processes, but we don't have the full set of evidence, and that's what we're hoping to gather as soon as we can.
Yeah. Thank you.
Craig, you're on mute.
Right. Thank you, Julian. I said, please unmute your microphones. No, I said we have time for one last question. So since you had your hand up, if you want to take the last question.
Yeah, I'll ask one last question. Margaret, you mentioned, of course, peat soils and drought are 2 of the key factors that are required here. But you also mentioned that there's been a period now of increased storminess during the winter periods. And so do you think there may be an association between perhaps, significant sea salt, stormy periods prior to these drought events that are maybe priming the systems? And have you looked to see if the intensity during the summer period is related to perhaps a heavier frequency of storm events during the winter period?
I don't think that's something that we have considered fully yet. And yeah, we can go back and look at the data. I think maybe looking at the records and seeing if we can piece that together a bit better. So that's something that we can go back and look at.
Great.
Thanks.
Okay, well, I guess then that will conclude today's session. Margaret, thank you so much again for kicking our seminar series off this year. I think is the next one in 2 weeks' time, Sarah?
Yes, we've got 2 in 2 weeks' time, so nothing
2
next
weeks.
week, but
Okay.
double bill next week. But yourself and
yes,
Ian
I'm speaking in 2 weeks' time. Yes.
Yes.
I'm
And
glad
also
someone
Neil
reminded
Robertson
me.
from
Wonderful.
Edinburgh University. We'll be speaking on the Tuesday. But yes, looking forward to that.
Fantastic. So I was going to put the website of the IIES on the chat, but I realized that everyone would have already gone there to register for this one. So there's no point to doing that. So please do check in again in 2 weeks' time. We've got 2 separate presentations. And yeah, we'll keep this going for the next sort of few months. And thank you all for logging in. And again, thank you to Margaret. I'm going to push the clapping hands here because you gave the first presentation. Thank you very much, and I hope you all have a good evening or day, whatever time it is, wherever you are. Bye-bye.
Bye-bye.